Hey everyone, we are going to go into the final lesson in Trig and its problem solving. Like I said, I've said before, I like Trig, and the neat part about Trig problem solving is it's got that same kind of flow as the problem solving we did before with rates. So yeah, let's get started. Put some bullets in here just to kind of help us out, and these are in your lesson as well. You got to draw a diagram, right? You got to draw a triangle and make things that are fixed, a number, and things that are changing, make them variables. And then as you read the problem, we always want to make sure that the number of variables we have always match the rates. And that's the same thing as we did in the last chapter too, like when you had the cone question, right? You had to make sure that the radius and the height were related to each other, and you had the right number of variables for the right number of rates. And then when you're doing triangles, we're used to working with sine, cosine, and tangent, but you don't want to forget that you have secant, cosecant, and cotangent as well. And sometimes working with the reciprocal identities actually is easier for finding derivatives. So we want to make sure we choose the easiest one to work with. And then after we have our variable, we have to put the rates in. And then the same thing we did with the last chapter of problem solving. You solve for the moment in time. So we have to be careful that when we talk about solving for the moment in time, that you don't put that moment in time into your original diagram, you leave it for a second diagram. And quite often as we're doing these problems, you're usually not given all the information. You kind of have to find one piece of the puzzle all by yourself. So question number one, you got the lighthouse question. And I had a nice lighthouse here, but instead I put a picture in instead, and I left my nice boat here. So the boat is sailing away at a speed of 30 kilometers an hour, which means the angle is changing, and which means this distance in the bottom is changing. This 2 kilometer distance is not going to change, right? So you're running parallel to the shore. So again, the lighthouse is keeping track of the boat over here. And we don't need hypotenuse in this problem. We're just going to deal with a couple of sides because how fast the boat's going and the fixed distance. So looking at that, again, if you look at your two rates, you actually have a tangent rate or a tangent ratio and a cotangent ratio, right? Opposite over hypotenuse or, sorry. How about we try that again? Two rates, tangent, opposite over adjacent, or cotangent, adjacent over opposite. And when you rearrange these, you can kind of see that solving it so you don't have fractions 2 tangent x, or you get a product x cotangent 2, or cotangent equals 2x to the minus 1. This is way too complicated, so we're not gonna solve with the complicated version. We're going to solve our rate with the easier to figure out rate. All right, so we put the rate in with respect to time. Derivative of tangent is secant squared. Derivative of theta with respect to time is d theta dt. So again, implicit differentiation. Derivative of x is 1, and the derivative of the x with respect to time is dx dt. So now we've got our problem set up, right? We did the triangle, we chose tangent, and we put the rates in. Now we want to solve for the moment of time. We want to solve when this distance coming straight up from the lighthouse, 2 kilometers, the boat is now 4 kilometers past the lighthouse. So how are we going to solve that? 2 secant squared d theta and dx dt. So in our problem then, we aren't given secant, and we're not given secant squared. So we got to find secant squared on our own. And there's a couple ways of finding secant squared. One way of finding secant is to do hypotenuse over adjacent and then square that. Now we weren't given the hypotenuse, so we had, for the moment in time, we found the hypotenuse. And then when you hypotenuse over adjacent and you square that, square root of 20 squared is 20 and 2 squared is 4. So secant squared using the old-fashioned hypotenuse over adjacent is 5. What I'd rather see you do, though, is I'd rather see you use what you learned back in Math 30, is that secant squared is 1 plus tan squared. And if you use this method to find secant squared, you don't have to find the hypotenuse because you're working with what's given to you. You're working with the 4 and the 2 that were given to you. So secant squared is 1 plus tan squared. Tangent is opposite over adjacent, so 4 over 2, which is just 2. So secant squared is 1 plus 2 squared, which is 5. This is my preferred method for figuring out secant squared. This is not wrong. I just think it's more work. So now we found secant squared on our own, and we can now go back to our equation, 2 secant squared d theta dt dx dt. Secant squared was 5, dx dt, the speed of the boat was 30. Plug everything in, 2 times 5 is 10, 30 divided by 10 is 3. D theta dt. We always solve our problem in terms of radians. We do not use degrees. Degrees are our unit, kind of like meters or kilometers, right? So when you do radians back in old math 30 there, you found out radians were arc length divided by radius. So there are no units in radians. So that's why everything you do in higher sciences, higher mathematics, is always related to radians. All right, so that's example number 1. I think that's a long enough video, and let's do a new video for the next examples here. Whoops, let me just fix that here.